We're beginning our look at non-homogeneous differential equations, and what we have here is one that has constant coefficients. So we've got a sub n, the nth derivative of y, plus a sub n minus 1, the n minus first derivative of y, and so on to a sub 1 y prime plus a sub 0 y is equal to g of x. And we're going to see two different rounds of dealing with these types of equations. This first one is something called the superposition approach. This is one of two ways to deal with an equation using something called undetermined coefficients, and we won't be looking at the other one in this course. In this case, we're looking at g of x, the right-hand side, which is sometimes called an input function and sometimes called a forcing function. But in this lesson here, we're looking at input functions that are constants, polynomials, exponentials, sines and cosines, and sums and products of these. We will see a different approach for different types of input functions than these. The reason we're considering this list is because when we differentiate functions in this list, we get functions that are basically in this list. So they differentiate to functions that are in the same category. I have here an equation that we did see in an earlier video. Y double prime minus 6y prime plus 5y is equal to negative 9e to the 2x plus 5x squared plus 3x minus 16. We already saw its solution, and what we saw was that the general solution is y equals c1e to the x plus c2e to the 5x plus 3e to the 2x plus x squared plus 3x. And essentially the 3e to the 2x is a solution because of the existence of negative 9e to the 2x in the differential equation, and the existence of x squared plus 3x is due to the existence of 5x squared plus 3x minus 16 in the original equation. You've already seen how to get the c1e to the x and c2e to the 5x. Now, finding this complementary function is a necessary first step for basically the rest of this chapter. The particular solution is a feature of non-homogeneous differential equations solutions and is the focus of this set of videos. So the particular solution exists because the right-hand side is different from 0. And here what we have is that g of x comprises an exponential function and a polynomial. And it's not necessary to break them apart in this way, but it is pretty much necessary to identify what they are, because the technique we're using right now only applies to types of functions that are in the list that I read before. Because of something called the superposition principle for non-homogeneous differential equations, we do actually get to consider forming the particular solution individually based on what we're seeing in the forcing function. So we're going to kind of tunnel vision this a little bit, and we're going to start with y double prime minus 6y prime plus 5y is equal to negative 9e to the 2x. Now, we already have the complementary function and you know how to do it, but I want to demonstrate proper technique. And the first thing we do is we deal with the auxiliary equation. M squared minus 6m plus 5 is equal to 0. So m minus 1 times m minus 5 is equal to 0. And so we have that m is equal to 1 or 5. And that's what gives us that y sub c, the complementary function, is that c1e to the x plus c2e to the 5x. Okay, that's not news, but here's what I said before. Dealing with the complementary function and solving an auxiliary equation and forming that solution is step 1 now. It used to be the entire problem, right? Okay, but now we have a right-hand side that is an exponential function. And so I'll call this g1 of x. Say it's like the first of the input functions from the bigger differential equation that we were looking at, is equal to negative 9e to the 2x. And at this point, it's useful to classify this, right? This is an exponential. And it's important for us to note that this exponent is 2x for a couple of reasons. Number one, we want to make sure that this 2x, this e to the 2x, doesn't match exactly any of the functions that we have in the complementary function. That is, we have e to the x and e to the 5x. Neither of those exponents matches e to the 2x, and so we're basically cleared to move on. If they did match, well, we'll deal with that later. Now, as I said, the reason that we're looking at this particular list, constants, polynomials, exponentials, sines and cosines, sums and products of these, is because when we differentiate these types of functions, we get back these types of functions. In other words, seeing that this is an exponential with an exponent of 2x allows us to make a guess. Now, it's an educated guess, but we're going to guess that the particular solution, I'll call it yp1 because, by the time we're done, we're going to have an entire particular solution with an exponential and a polynomial. And of course, by the way, when you start this process, you don't usually have the answer in front of you, right? So we're just seeing where that comes from. Anyway, we're going to guess that this has a form of e to the 2x, although the function e to the 2x could have a coefficient different from 1, and it's basically our work to figure out what that coefficient is. So we're going to put a variable in there. We're going to call it uppercase A, and it matches the form of g1 of x. Now here's what should be, by now, a pretty familiar pattern. We have a form of solution. We're going to plug it into the differential equation and see what we end up with. If yp1 is equal to ae to the 2x, then yp1 prime is equal to 2ae to the 2x, and yp1 double prime is 4ae to the 2x. And this is going to go into the differential equation, but the one we tunnel vision that only has negative 9e to the 2x on the right-hand side. So we've got 4ae to the 2x for y double prime, minus 6 times y prime is going to give us minus 12ae to the 2x, plus 5y is going to give us 5ae to the 2x is equal to negative 9e to the 2x from the right-hand side. E to the 2x is in every term, so we can basically dismiss it. And on the left-hand side, we have, what is that, 9 minus 12, so negative 3a in the right-hand side equals 9. Therefore, a is equal to 3. And we had proposed that the solution should look like ae to the 2x. We just found that a is equal to 3. And so we have that yp1 is equal to 3e to the 2x. This a that we started out with was a coefficient that had yet to be determined. And folks, that's why this is called undetermined coefficients. Now, if we look at the other part of the input function, we can consider that we have y double prime minus 6y prime plus 5y is equal to 5x squared plus 3x minus 16. This is the polynomial part. And for this polynomial part, I'm going to identify g2 of x as that 5x squared plus 3x minus 16. And we can see here that this is a second degree polynomial. So we're going to write down a form of solution yp2 to correspond to g2 that's in the form of a second degree polynomial. We want it to be a generic second degree polynomial, so all the terms need to be accounted for. We used a before, but we already figured out what a is, and we're not going to be using it in this context presently to mean two different things. So we'll just go ahead and reuse it. It's fine. And we have ax squared plus bx plus c as our generic second degree polynomial. Now, what I'd like you to do is what I just did. Take this form of solution, ax squared plus bx plus c, plug it into this differential equation, y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16, and see what you can get for the values of a, b, and c. I'll talk you through what I've got. Y double prime is 2a. Negative 6y prime is negative 12ax minus 6b. And 5y is 5ax squared plus 5bx plus 5c. One of the more common things to do is to forget to distribute the negative 6. On the right-hand side, we have our 5x squared plus 3x minus 16. And now what I'm going to do is what I've done is gather together all the x squared terms on the left and right, so I can see that 5ax squared equals 5x squared, thereby giving that a is equal to 1. At this point, it maybe feels a little bit like partial fraction decomposition. I think that's appropriate. For the x terms, we have negative 12ax plus 5bx on the left is equal to 3x on the right. Substituting 1 in place of a and solving, we get that b is equal to 3. And finally, for the constant terms, we have 2a minus 6b plus 5c is equal to negative 16. Again, since a is 1 and b is 3, we can solve and find that c is equal to 0. The form of our y sub p2 in this case, was ax squared plus bx plus c, and we found that a is 1, so x squared, b is 3 plus 3x, and c is equal to 0, and that's where this x squared plus 3x came from that we saw earlier. The overall particular solution is the sum of the individual particular solutions, and we saw that before, and it was called the superposition principle for nonhomogeneous differential equations. And so in this case is going to be 3e to the 2x from the first round of this plus x squared plus 3x from the second round. That together with the complementary function gives us our solution. So in symbols, we have y is equal to yc plus yp. In this case, if I remember right, the complementary function is e to the x plus, c1 e to the x plus c2 e to the 5x. And now throwing that together with this particular solution gives us that 3e to the 2x plus x squared plus 3x as our final solution to the differential equation. This is basically how it goes. Looking at just g of x from the original differential equation, it was negative 9e to the 2x plus 5x squared plus 3x minus 16. We could have used as our particular solution y sub p is equal to ae to the 2x for the exponential part plus bx squared plus cx plus d for the polynomial part. I wouldn't reuse a in this case because that would imply that those two coefficients were the same. Doing this, it's about the same work. It's more to write it in individual steps, but you get to do it all at once. It's a wash.